So let's start by describing position, and then we'll move up to the velocity field. So let's talk in Cartesian coordinates, where we can have, say, an x, y, z system, x, y, and z. And we're going to talk about position in a way that you've probably seen before. And so we could say that a particle has position in vector form. We could call it like an r vector. So there's our little particle with its position, and we'll write that as position. We could give it a little r hat, like a little r vector, and that can be a function of time. And just so you see here, this is kind of projected down. Maybe it's a point that looks like this at that particular instant in time. And that position vector, we've got our unit vectors that look like in the x, y, z, we've got a little I hat going this way, a little unit vector in the y direction that we can call j hat, and a little unit vector in the z direction called k hat. And so I can represent the position of a particle using r of t in vector notation. And so this has a magnitude of x in the I direction plus a magnitude of y in the j direction and the magnitude of z in the k direction. And so this is the vector notation to represent this point in space. That's all we're talking about. But what's interesting is that each of these is actually a function of time. And so another way that we could kind of expand the way we wrote this is to call it x of t, just to remind ourselves that all of these things are varying as a function of time. Y of t as a function of j, or plus times j there, magnitude, direction, and z as a function of time in k hat. Now we don't know what these functions are yet, but there could be one. And you could imagine that at some other time that particle has moved, say, up here. And what that would give us is a new position vector that looks like this. Okay, so this would be, say, whoops, wrong symbol there, get rid of that, r at time t plus, say, dt, some little time step forward. Our particle has moved. How'd it get there? Well, we don't know exactly, but there's some sort of a path that it's taken. Maybe that path looks like this. So it's flowing along some path, like a streamline maybe. And once again, these are projections, and so it's a little tricky to draw in 2D, but you could imagine that this is something out in this region here. So if we want to talk about the velocity of this particle, the velocity of particle, you can remember from dynamics class, the velocity is just the derivative of the position with respect to time, and the same holds true here. Velocity is equal to the derivative with respect to time of the position, which is this r hat, or r of t. And so if we take the derivative of this position vector with respect to time, we get a thing that looks like dx dt I plus dy dt j plus, you guessed it, dz dt k. Essentially velocity components in the x, y, and z direction. This part really is the same as continuums or solid mechanics, so that, or point particles, that kind of thing. But we're going to give each of these a name. So we're going to call the x component u. This is just a convention. You can call it anything you like. We're going to call the y direction little v, lowercase v. We're going to call the z direction w. And so we can rewrite this, that our velocity vector v is equal to, say, u, but u now is also a function of space and time. And so u of x, y, z, and t times I hat plus v of x, y, z, and time of j hat, and w of x, y, z, time k hat. Something we might like to talk about as we work with this is the magnitude of the velocity. Right, just how fast is it going? We can write that in vector notation as the magnitude of the velocity, which would be just the sum of the components square rooted. U squared, v squared, plus w squared, and you take the square root of all of that. So just to give you a little concept idea here, if we had, say, an airfoil and flow approaching it, all we're saying right now is that at any point we can write a velocity vector that looks like this stuff. And so this is one here, velocity of, say, we could call this r1, and this one over here could be some other point, so this would be the velocity of, say, point r2, location r2. Should write these with vector notation. The idea here is just that the velocity can vary with position.